Hello everyone. Now this is part 2 of lecture 10. Now one thing, in the previous part of lecture 10, that is in part 1, I have made a mistake and one of my student has pointed out that error, and that mistake you can find it in the said lecture at around 20 minutes 45 seconds. So go to the playlist Electrochemistry and you find there lecture 10. You go to part 1 lecture, and at around 20 minutes 45 seconds you can see I was writing a Nernst equation for the electrode half Cl to Cl minus. So the reaction was like half Cl2 plus electron arrow Cl minus. The Nernst equation should be, this is the EMF of the single electrode and this is the same but in standard state. Since it is a single electron transfer reaction, so here we will put 1 instead of in place of n, and here it will be log product by reactant. So in the numerator we will get Cl minus third bracket, that is concentration of Cl minus in the electrolytic solution, and in the denominator I have mistakenly placed PCl2. So since I was thinking on the fly, I sometimes make mistake. So this is the first mistake that I have made in the video, and please correct it, and for the betterment of you, so that you can easily rectify it, I have written the problem, I have solved the problem on a piece of paper and I have uploaded it to Google Drive, and I have put the link in the comment section and also in the description box. So go to the description box, and using that link, by clicking on that link, you just download the hard copy. So you'll get the solved problem. Now again, I am solving it for you. So the mistake I have done is I have continued with this form. But see, if I continued with this form, you have to write here square. Since if you write Cl2, then you have to write plus 2 electron and then here 2 Cl minus. Then here you have to write 2, you have to write here square, then only you can write PCl2. But if it is in this form, here it will be Cl minus third bracket to the power 1, and here it will be 1 since it is single electron transfer, and here it will be to the power half. I missed this part. So make it correct, or another alternative I have given to you, that is you just click the link in the description box and you download the paper where I have solved it for you. Now if you continue it, you see this was given plus 1.36 volt, and it will be 1 here, so it is 0.0591 log, and it is Cl minus concentration, I cannot remember. So now you know the method was given in that part. Just I could remember that pressure was 5 atm and it was 0.15 maybe. So what you have to do, you have to continue from this line, just having a power half over this pressure of Cl2. So it will be 5 to the power half, that is root 5 instead of 5. So it will be root 5. So please make it correct. I am sorry for the inconvenience caused to you. Now this is part 2, and here we have another problem. Find the equilibrium constant for the disproportionation reaction 2Cu plus reversible Cu2 plus Cu, and given Roman 1 one set of data, Roman 2 another set of data. So you have to perform two different solutions, and using these two different sets you have to find actually the equilibrium constant for this disproportionation reaction. Now one thing, the reaction given is same for both the sets of this data, both the data sets. So if the reaction is same, then the answer must also be same. This is the point. They are giving you different sets of data. In Roman 1 you could see that it is standard EMF Cu2 plus Cu and Cu plus Cu, and in Roman 2 you could see that here it is standard EMF of Cu plus Cu and Cu2 plus Cu plus. So this one is matching, this Cu plus Cu is matching, but these two are not matching. So these two are different sets of data, but you have to find the equilibrium constant of the same reaction. So the answer must be same, since a particular reaction cannot have two different equilibrium constant at the same temperature. Since they are giving you two different data sets, obviously temperature must be kept constant, and it is 25 degrees centigrade. Hopefully I have missed it, or if it is not given in the problem, just consider it, no problem, no issue. So do you understand the problem? So the answer will be same. Now you have to start with different set. So it will be the course which will start with different initial position, but actually will lead to the same destination. So let us see how the solution looks like. So let us first divide it into two sections. Here I will solve it for data set 1, and here I will give the space for data set 2. Now see, reduction potential is given, you can see it, Cu2 plus 2Cu, that is reduction. This is also reduction. So we will use the reduction method to determine the cell reaction and also the Nernst equation if needed. Now the reduction potential of Cu plus Cu half cell is plus 0.53 volt, and that of Cu2 plus Cu half cell is plus 0.34 volt. So which one is greater? Which reduction potential is greater? This one. 0.53 volt is greater than 0.34 volt. Now if the reduction potential is greater, it will have a greater tendency to be reduced. So simple. It is having a greater reduction potential. What does it imply? It implies that it will have a greater tendency to be reduced compared to this. So if we use the reduction format to have the cell reaction, then we have to subtract anode reaction from the cathode reaction. So let us first put cathode reaction. So cathode reaction, this one will be the cathode. Since it has a greater reduction potential, tendency of reduction will be greater. So when we connect these two half cells to get a cell, complete cell, reduction will occur in this half cell and oxidation will occur in this half cell. Reduction potential is greater, I am repeating. So tendency of getting reduced is greater. So when I will connect these two half cells both internally with the salt bridge and externally with the conducting wire, then this electrode will suffer reduction, and at this electrode oxidation will occur. So if we use the reduction format, then we must subtract the anode reaction from the cathode reaction to get the positive value of standard EMF. So the cathode reaction will be simple Cu plus electron arrow Cu, and the voltage is E0 Cu plus Cu equals to 0.53 volt, this one. And the anode reaction, it is, what is the anode? It is Cu2 plus 2 electron arrow Cu, and the standard EMF is E0 Cu2 plus Cu equals to 0.34 volt. Now see, this will not cancel out the number of electrons. So the number of electron transfer is not balanced. So we must perform it. So we multiply here by 2. So it will be 2 electrons, it will be 2 Cu. Now at this point one may ask that whether I have to multiply this standard EMF by 2, whether I have to do it or not. So in previous lectures, maybe in lecture 8 or 9, I have told you, and I have not just told you, I have shown you that writing it in this way, or 1000 Cu plus 1000 electron arrow 1000 copper, is not going to affect the potential, because if the electromotive force depends on your way of writing, that would be amazing. You will be a magician. Okay, so nature will not be controlled by you. You cannot control nature in that way. In that way you cannot control it. That you are writing here Cu plus electron arrow Cu, so it is, that cell is giving a some voltage, say X, and you are just writing on the paper that it is 2 Cu plus 2 electron arrow Cu, then it has started giving another voltage. So that is unacceptable. So this multiplication will not be carried forwarded to this potential. This will remain the same. Okay. If you have any queries, feel free to contact me. My email ID is alendu2007@gmail.com, and also in the comment box you are free to discuss. No issue. Now I have told you that if we continue with the reduction format, then we have to subtract anode reaction from the cathode reaction to have the positive value. Now if we subtract, this will cancel. Don't cancel it in exam, it will be childish, and if you cancel it, use a pencil. So it will be 2 Cu plus minus Cu2 plus arrow Cu. Check whether I am correct or not. I am thinking on the fly, so there may be error. So please cooperate with me, and you also check whether I am correct or not. If there is any wrong, like my student, you please comment on the comment box. Now see, 2 Cu plus 2 electron arrow 2 Cu, and it is Cu2 plus 2 electron arrow Cu. Now this 2 electron cancels out. Here it is 2 Cu plus minus Cu2 plus 2 Cu plus minus Cu2 plus arrow 2 Cu minus Cu, that is Cu. So rearranging, we will get 2 Cu plus arrow Cu2 plus Cu. This is the cell reaction. And see what they are giving you. They are giving you this reaction, 2 Cu plus reversible Cu2 plus Cu. Now why they are calling it as disproportionation reaction? Because you are getting two different oxidation states from a single oxidation state. See here it is only one kind of oxidation state, that is +1, and from it one cuprous ion is getting oxidized one step to give you cupric ion, one cupric ion, and another cuprous ion is getting reduced to give you the metallic copper. So if I write it in this form, it will be clear to you. I am writing this 2Cu plus as Cu plus plus Cu plus. Arrow Cu2 plus Cu. So you can see here it is oxidation by 1 electron. See, cuprous is getting converted to cupric. So it is 1 electron oxidation. It is getting oxidized by one step. And this electron is being accepted by this Cu plus. So here it is one step reduction. And it is giving metallic copper. So from one kind of oxidation state, that is +1, you are getting to different oxidation states +2 and 0. That is a case of disproportionation reaction. So the cell reaction is the disproportionation reaction, and they are asking you to find the equilibrium constant for that reaction. Now what will be the procedure for data set 2? Here see, the reduction potential for copper plus 2 copper is 0.53 volt, and for copper 2 plus 2 copper plus is plus 0.15 volt. So here reduction potential is given, see, plus 2 to plus 1, and here it is plus 1 to 0. So both are in reduction potential. Now this one has a greater reduction potential. What does that mean? It means that tendency to get reduced is greater here than here. So when we connect these two half cells internally and externally to get a complete cell, reduction actually occur in this half cell and oxidation will occur in this half cell. So it will act like anode and it will play the role of cathode. Do you understand? Simple logic. So again, cathode reaction we have to write it first in case of reduction method, and in case of oxidation method you have to write anode reaction first. So cathode reaction is this one will play the role of cathode, so it will be Cu plus plus electron, Cu plus plus electron, arrow Cu, and the voltage given is E0 Cu plus Cu equals to 0.53 volt. And in anode, what it will be? It is Cu2 plus Cu plus. So Cu2 plus plus electron arrow, Cu2 plus plus electron arrow Cu plus. And this value is 0.15 volt. Check whether I am correct or wrong. Now I have told this several times in the previous lectures that one may ask, and you people may also ask, that in anode oxidation is occurring. You have just now told that in anode oxidation occurs and you are writing reduction here. Why are you misleading us? No, I am not misleading you. It is a formality. How? When you use the reduction format, you have to maintain it in the entire course. And when you use the reduction oxidation format, you have to enter the oxidation in the entire course. Now, since here we are following the reduction method, we have to write the reactions that are occurring in cathode and anode both in reduction form. So here you see this is reduction, acceptance of electron, and here in anode it is also acceptance of electron. So both I have written it in the form of reduction. Now in anode what happens? Oxidation occurs. Now since in anode oxidation occurs, I will put a negative sign here. I will subtract anode from cathode. So this minus, when you try to incorporate in this reaction will get reversed. And when it will get reversed, what will happen? This will actually look like Cu plus, this will come here, Cu plus arrow Cu2 plus plus electron. So that is what you want, that is oxidation is occurring at the anode. So I am telling the truth, I am I'm implementing the truth also, but in a way that is not that simple. So that is our limitation, that we cannot make a hodgepodge. Different types of format must not be implemented in a single method. So do you understand that I am writing it in reduction form, but I will subtract it finally, so that this reaction will get reversed and will add up. So if this reaction is reversed, then it will look like oxidation. So no problem. I have nothing done wrong. No injustice has been done. So this cell reaction, and this is minus, minus, minus. See, here I have to multiply this half cell reaction on both sides by 2, since there was a 2 electron transfer here. But so here I have to write n equal to 2. But in this case there is no 2 electron issue, so I have not multiplied here by 2. Now this will be Cu plus minus Cu2 plus arrow Cu minus Cu plus. See, this electron will cancel out. It will be Cu plus minus Cu2 plus. It will be Cu minus Cu plus. Or rearrange it. This Cu minus will come here. So it will be 2Cu plus arrow. This will go to the right hand side. It will be Cu2 plus plus Cu. Now see, using the different data sets, you are able to arrive at the same cell reaction. That's why they are asking you to find the equilibrium constant for the disproportionation reaction using 2 different sets, because this can be done. Now what is the procedure to find the equilibrium constant? I have find the equilibrium constant in 2 previous lectures. Now that is not very tough. We know del G naught equals to minus RT ln. Ln means log natural. It is K equilibrium equals to minus NF E naught cell. So this E naught cell or E0 cell, it is the standard EMF of the cell. This F is the Faraday, N is the electron transfer, and R is the universal gas constant. It is the absolute temperature. It is the equilibrium constant. This is the connection. I have shown it to you previously in previous lectures. So ln K equilibrium will be, you take this here, so it will be minus NF E0 cell by minus RT. Is it okay? Now E0 cell by RT upon F. Now when log natural is replaced by log base 10, it will give you a factor 2.303 here, and I am taking it to the right hand side, so it will be N E0 cell by 2.303 RT upon F. This is the formula. Now at 25 degrees centigrade, you may pause the video and take the note of it, or you may take screenshots to make note. Please make note and try to solve it for yourself. If you don't practice of your own with pen on paper, if you just see this video, it will not going to work in exam. To reproduce it in exam paper, you have to practice the problem of your own. Repeatedly you have to read and practice multiple times. Now log K equilibrium equals to, this is N E0 cell. Now see, at 25 degrees centigrade, this product will give you this 2.303 RT by F, this expression will be 0.0591, 2.303 RT upon F. So this is the expression for K equilibrium at 25 degrees centigrade. If the temperature is not 25 degrees centigrade, you just put the value here, no problem. 2.303 into R, it will be 8.314, and you put the temperature that is given in obviously in absolute temperature, so you have to add 273 to 25, and it is 96500. So we will get this value. Now it is showing you that to have the equilibrium constant, you must know the value of E0 cell. Now you are getting the cell reaction by subtracting the anode reaction from the cathode reaction. So you will get the E0 cell by subtracting in the same procedure. You are getting the cell reaction by subtracting the anode reaction from the cathode reaction. So you will get the standard EMF of the cell just by subtracting the corresponding anode reaction from the cathode reaction. That's why I have written the half shell reaction in the way it is given. They are suggesting reduction potential. Hence, I have written it in the form of reduction. They have given reduction potential, I have written it in the form of reduction, and then I have organized it in such a way that we get the cell reaction. So the way in which we get the cell reaction, that way must be carry forwarded to determine the EMF of the cell. So if we subtract here anode reaction from the cathode reaction, here also we will subtract the standard EMF of anode from cathode. So that will give you the standard EMF of the cell. So it is 0. Let us remove it. I am sort out of place. So it is 0.53 volt minus 0.34 volt. So it will be, it is 943, it is 1, so it is 0.19 volt. Please check it. 34, and it is 0.19 volt. Now here also the E0 cell will be obtained when we subtract this E0 Cu plus, we will subtract E0 Cu2 plus Cu plus from this E0 Cu plus Cu. So it is minus E0 Cu2 plus Cu plus. Now you put here 0.53 volt minus 0.15 volt. 0.15 volt. Let us find out the difference. So it will be 0. This is 8.3. So this is 0.38 volt. So the data sets that have been given to you are giving you different value of E0 cell. Different value of E0 cell. In this case, that is with the data set 1, the cell that is constructed using these two half cells, the cell will have a standard EMF 0.19 volt. And as per the data set 2, the cell will have a standard EMF 0.38 volt. Now, see the formula, the expression that we have obtained, which relates the equilibrium constant with the E0 cell, is this. Now see, two different EMF have been obtained. Two different EMF have been obtained. Now at this point, I was astonished that I have to find the equilibrium constant for the same reaction. So the value must not change so long as temperature will remain constant, and I have put the temperature, same temperature in both the cases, so that this formula will also work here. Here also log K equilibrium will be N E0 cell by 0.0591. So The same temperature will rule here. Now same reaction in both cases, but different cell EMF. And the relation between the equilibrium constant and the cell EMF, standard EMF of the cell is this. So isn't it giving you the signal that different E0 cell will give you different equilibrium constant? So if you put here 0.19 and if you put here 0.38, that will give you different value of the equilibrium constant, but that must not be, since you are dealing with the same reaction and you are dealing it at the same temperature. So same reaction, same temperature, equilibrium constant must be the same value, must be of the same value, but you have two different value of E0 cell. Then how will you get the result? So this is the beauty of nature. See, since the data set is different, since the E0 cell is different, nature has adjusted it in such a way that it will not give you different value of equilibrium constant, and that must not be at a particular temperature for a particular reaction. You cannot have two different equilibrium constant. So see that this expression is associated with N, that is number of electron transfer. So you see here it is 2 electron transfer, so it is N equal to 2, and here it is 1 electron transfer, so here it will be N equal to 1. Now you put the values, this is N equal to 1 into, this is 0.38, and here it is 0.0591, and here you put the values, it will be 2 into 0.19 and it is 0.0591. So you see 0.19 into 2, it is actually 0.38. So you have to use the calculator here. Now 0.19 into 2 equals to this one divided by 0.0591. So it is 6.429 78. Now I am finding this one. You need not to find this. See, 2 times 19 is 38. So this will also give the same value. Still don't believe it. Use the calculator and determine the value. So this will be also 6.42978. So you can see that you cannot play with nature. This problem is actually trying to play with nature, that I will confuse nature so that there will be two different voltages, but I will get the identical cell reaction. So different voltages, different EMF will try to give different cell, different equilibrium constant. Then I will ask nature that you are wrong, but nature is hyper intelligent and it has adjusted it with the value of N. So when you are getting 0.19, nature is multiplying here by 2, and when you are getting 0.38, it is multiplying it by 1. So you cannot fool nature. If you fool nature, it will pay back you with interest. Okay. So what will be the value of K equilibrium then? The value of K equilibrium will be 10 to the power, this is base 10, so 10 to the power 6.42978. This will be 10 to the power answer, 10 to the power answer. 1, 2, 3, 1, 2, 3, 4, 5, 6. So it is 2.69 into 10 to the power 6. 2.69 into 10 to the power 6. Please check it. So this will be the value here. Same thing. So here K equilibrium will be 2.69 into 10 to the power 6. This will be the value of equilibrium constant at 25 degrees centigrade for this reaction. Now you have obtained the value of equilibrium constant, and this is the question, that find the equilibrium constant. I will suggest you not to leave the problem here. You leave the problem in exam paper, but when you are practicing it at home, think of it, that what value you have obtained. Please check these values. I am repeatedly saying that I am thinking on the fly. I may be incorrect while carrying out the calculations, but my procedures are correct. Obviously, there are no error within the procedures. So, the value obtained is 2.69 into 10 to the power 6. I am requesting you to focus on the value. What extra information it is giving you? You see, equilibrium constant is given by product. So, equilibrium constant, let us write here. We will get more space here. So, equilibrium constant will have the same value for both the cases, since the value is same, 2.60 10 to the power 6. Okay, so I am removing it for the necessary information that we are getting from this value. So, K equilibrium for this reaction will be ACU. Now, the activity of pure solid is 1. So, it will be product Cu2 plus by Cu plus third bracket whole square. Since here it is 2. Now, if it is of the order of 10 to the power 6, then it will imply this, that Cu2 plus is almost equal to 10 to the power 6 times that of Cu plus whole square. So, you have started with Cu plus. You have started with Cu plus. See, you have started with Cu plus, and at equilibrium, when you get the equilibrium, you are noticing that the amount of product that is formed after attainment of equilibrium is million times greater than the square of the concentration of the reactant. So, product is million times greater than the square of reactant. So, what does it imply? That the reactant has almost finished. So, this guarantees, this high value of equilibrium constant guarantees the almost completion of the disproportionation of the given disproportionation reaction. So, high value of equilibrium constant means the reaction has almost completed. So, this message you must carry in your mind. Okay. Okay, thank you. Stay with me. I will come back with another problems in part 3.